Hello. Good afternoon, everyone. Thanks for coming. Welcome to the latest installment of the department's Conservation Lecture Series. My name is Tom Lupo. I'm Deputy Director for the Data and Technology Division, and I'm going to introduce this topic and our speaker for this afternoon. You know you're here for ACE, Areas of Conservation Emphasis. What you might not know is that this is not a new product. This is not a new effort on the part of the department. This is something that's been evolving, let's say, for about the last 10 years. This is now the third major iteration of it, third major architecture. Version 1 was paper maps, hand-drawn, what we used to call the bubble maps, right? So that was early days, early thinking, limited utility. It from there morphed into a digital thing that was more data-based rather than expert knowledge, expert testimony. And the data have been refreshed multiple times over the years, and now this is the third major architecture for it. And the point of this, going back 10 years ago, back when in the early days of this, is that the department was often in meetings or discussions with other organizations that had long-term visions about what the state of California should look like for them, right? Caltrans had their sort of 20-year plan, and Department of Water Resources and Housing and Community Development and Nature Conservancy and lots of other collaborators and partners had a plan. They had a map. And we never did. We never had anything that we could roll out or present that would say, this is our view of what the ideal California would look like, that would fully reflect all of the mandates and legislation and priorities that the Department of Fish and Wildlife had. Right? And so we were not such great partners in that regard. So that was what was driving this, is could we somehow put down on paper the things, the areas that were of most importance to us? And, you know, you guys know this is a complex department, right? We're bifurcated. We're schizophrenic between conservation and consumption. And we're also data poor in some areas. So what we have here today is the next evolution. You know, 10 years we've been thinking about this, but we're not done. This will really probably never be done. Every year we get new data. Every year we get new mandates. We get new legislation. So we're constantly evolving this as sort of a language of what's important to this department. This is a big one. This is a big step forward here. Our speaker today, Dr. Melanie Gogol-Prokurat, has been involved with this from the beginning. She was there with the first bubble maps. I think we spent a lot of time at Fox and Goose talking about how could we do this, right? Some things never change, right? And so she's been through this with every iteration. And this is a part of Melanie's job, to be the ACE coordinator. But really her job title is that she's the Conservation Analysis Unit Coordinator, or I think your working title is Spatial Ecologist, which to me is like one of the coolest job titles in the department, spatial ecologist. It sounds like some sort of a superhero or something. I want that job. So she works with all things spatial data, GISE, with an ecology focus. So connectivity, climate change, vulnerability assessments, ACE, conservation planning support kinds of things. So she's, an in-house think tank, so to speak, wrestling with the big issues that are facing the department. Finished her PhD at UC Davis in 2009. Where'd you do undergrad? UC Davis, so yeah. Really? All right. Anyway, so Melanie, thank you.
All right, thanks, Tom. Okay, so I'm going to be going over a lot of information today about ACE, starting with an overview. I'm going to do the what, so what is ACE and why did we create it, the where, navigating ACE and where to find the information. Then I'm going to get into the nitty-gritty with all the information about the ACE model, what data sets are available and how they were developed. and then how, so example scenarios, how to use the data in Viewer, and then finishing up with where we're going in the future. So we'll talk first about the goals and purpose, and Tom mentioned some of this already. So ACE brings together information from a lot of our California Department of Fish and Wildlife, or CDFW, mapped data products, including the California Natural Diversity Database, CNDDB, the California Wildlife Habitat Relationship System, or CWHR. I'm using a lot of acronyms today, so I'm trying to define all of them, and I'll try to use the whole name as much as I can. And the Survey of California Vegetation, which is our department's vegetation maps. And so ACE tries to bring together our best available conservation relevant spatial data, or map-based data, into a set of non-regulatory maps and a viewer tool that is freely available online that anybody can use. And so it provides a course level view of information that might be important for conservation planning purposes. So we want to make sure that we have all of the information that we need and that we're not missing anything really obvious. So bringing it all together in one spot so that we can look at it all at once can help with that. A lot of people have worked on ACE. Tom mentioned this, but so Karen Miner was the head of our working group, and our working group, there were too many people involved to even list on the slide. There were people from all branches and programs within our department. There was a development team that has been meeting weekly for the past year to develop all of the data. It's all been scripted by our scripting duo, who did a great job scripting everything so that we can refresh the information with new data very quickly. And then also our viewer developers. So ACE is on our BIOS platform, and that has been developed in-house. And so a lot of work went into customizing that for the ACE viewer. So a little bit of history, as Tom mentioned, it's been about 10 years since we first put ACE2 online, and that focused on biodiversity and significant habitats and has been updated about annually. But this new version is a major update. And so I just also wanted to mention the ACE2 development team, who developed a lot of the biodiversity and significant habitat metrics that we are still building on today. So ACE version 3, we've been working on it for about the past year, and there's a few major changes that we've made. So one thing that we did was we separated out terrestrial and aquatic data so that you can look at them separately. We've revised and added new models, particularly connectivity, climate resilience, and recreation. And then we also added our 2015 State Wildlife Action Plan, or SWAP priorities. So here's a quick little diagram of the data structure in ACE, and you can see this on our webpage. This shows all the major components. So there's biodiversity, significant habitats, connectivity, climate resilience, and recreation. So it shows all of the pieces and how they fit together. So there's an overarching biodiversity and significant habitats layer, but then you can drill down further if you're interested in getting more detail. You can break it up into terrestrial and aquatic, and you can further break it down into information for specific taxonomic groups. And we've developed these icons, which you'll see on the website throughout the presentation today and in all of the ACE documentation. So that gives you sort of a visual reference of what data set you're looking at, because ACE includes a lot of different data sets, and it can be a little bit overwhelming at times. Oh, whoops. Also on the website, we have SWAP, we have stressors, and then we have land conservation status. So the analysis units that we used in ACE for the terrestrial data, we used a hexagon grid. So that's a standard size across the landscape. They're 2.5 square miles in size. So that's about one line of the hexagon is about a mile in width. The aquatic data is HEC 12 watersheds, and so those are from the National Hydrography Database. They're variable in size. They range between 4 and 425 square miles, so there's a lot of variation in size. But the mean size is about 38 square miles, so quite a bit larger than the terrestrial hexagons. But they're a good unit to compile aquatic data. The other unit that we used for the terrestrial data was USDA ecoregions. And so these break up the state into units that are similar in habitat type, topography, suites of species that are present. So they're ecologically based regions of the state. And all of the ACE data, when you look at it in the viewer, it's colored from yellow, green, or blue. And so all of the data in the viewer is ranked from 1 to 5, where 1, which is yellow, would be lower conservation value based on the analysis, and 5, which is higher, would be higher conservation value. The ranking for the species data is based on quantiles. And so what that means is that approximately 20% of the hexagons are in the highest 20% of the hexagons are in the highest category, so rank 5. The lowest 20% are in rank 1. So approximately 20% of the hexagons are in each rank. So what that means, since the hexagons are standard size, is that approximately 20% of the area of the state is in each rank. Another thing to note about the ranking is that we used the ecoregions to normalize the data. And so if you look at, for example, this is native species richness on a statewide basis. You can see that there's very high richness along the coast and in the north coast, and low richness in the southeastern deserts of the state. And that's because it's very different habitat types. They're not really comparable. And if you want to use this information for conservation planning, it's not really useful to have every single hexagon in your entire region ranked as a 5 or as a 1. And so to help correct that, what we did was we put the ecoregion sections over the data, and then we ranked the data within each ecoregion section. So the data is ranked from 1 to 5 within each ecoregion. So that helps you pull out the higher value areas within the desert and the higher value areas in the north coast. So aquatic was also ranked similarly from 1 to 5. It was not normalized by ecoregion, so it's ranked on a statewide basis using the same color scheme. So moving on to navigating ACE, where to find the information. I wanted to talk about this up front in case anybody has to leave early. All the information that I'm talking about today is on our webpage. And so we have a web page, we have fact sheets with information about each data set, and then we have the web viewer. So I'll talk about those 3 things right now. Our ACE website, you can get to it from our main CDFW webpage. If you click on the conservation tab at the top, that'll take you to the conservation page. And under CDFW laboratories, about 4 down, you get to conservation analysis. And so you can click on that to get to the ACE page. You can also just type ACE CDFW into Google, and that'll take you straight to the main ACE webpage. So there's one ACE webpage, so all the information is on this single page. And you can see here in the middle is the diagram that I showed you earlier with all of the symbols, the icons. And then below that is an accordion with more information about each of the components of ACE. So if you select something from there, you can expand it. You see the icons again, showing you what you're looking at, and then you can also click on a fact sheet to open the fact sheet. So the fact sheets are mini reports about each data set, and for GIS people, they're sort of like metadata on steroids. So in there, you can find all the information that you might want to know about the data set. So you can look at the data sources and models used, the data processing steps and ranking criteria, how to use the data layer, a list of the fields available in the data layer and their definitions, information about data precision and limitations, data access, and then acknowledgements and a bibliography. So that's a first, if you're looking at a data set and you have questions about it, that would be the first place to go. It would be to the fact sheet, and hopefully it addresses most questions about the data set. From the web page, you can also get to the ACE viewer, and so the launch button is up on the upper right. There's also a viewer guide available there, and there's also a link to download all of the GIS data. So all of the ACE GIS data is freely available for download. If you go ahead and launch the ACE viewer, you start out on this splash page, and there's two buttons here. There's one that says login and one that says use public ACE. So if you use public ACE, that will get you to all of the ACE data sets. So there are no ACE data sets that you need to log in to look at. The login button is for people who have CNDDB subscriptions. So as I'll talk about in a minute, you can overlay BIOS data sets onto ACE now, and one of those is CNDDB. So if you want to be able to overlay CNDDB onto ACE, you need to log in using your login and password. So when you open up the viewer, this is what it looks like. And so there's a table of contents on the left. There is a search box where you can add BIOS data sets. There are some map tools. There is a slider bar for changing the transparency of the data layers. And then there's a help button. So I'll just go through these really quickly. Within the table of contents, some important points are you can toggle between the ACE data sets, but you can only turn one on at a time. And one of the reasons for that is because they're all colored using the same color scheme, and they're all using the same units of either hexagons or watersheds. So if you turn on more than one at once, it can start to get very confusing about what you're looking at. So we've set it so that you can only look at one at a time. Because of that, if you want to turn off the ACE data, for example, if you're adding a BIOS layer and you want to turn off the ACE data so that it's not obscuring your view, you have to turn it off at the top there. The active layer, which is a layer that you can select on, is highlighted in pink. And then there are the ecoregions and the watersheds that were used in the ACE analysis that you can overlay on top of the data. You can also change the base map at the top, and there are additional reference layers down at the bottom. So if you want to add BIOS data sets, you can use the search box. And if you click in there, it'll give you the list of BIOS data sets. There's over 2,000 data sets in BIOS now. And if you type into there, it'll start to narrow down the list of what you're looking for. And so any of these you can overlay into the ACE viewer. That being said, they actually overlay underneath the ACE data, and so if you want to be able to see them, you either need to reduce the transparency of the ACE data or turn the data off. And so you use the slider bar, the opacity slider bar, and that'll lighten up the data for you. And finally, the map tools. So those are found at the top. You can, there's a number of different map tools, both regular map tools and advanced tools. If you want to locate a place on the map, you can go to GeoFind, and that will, you can type in coordinates or an address and get to a specific place on the map. So that was just a really quick overview of how to use the viewer. The help button up in the corner gives you a link to tutorials and trainings. So that is where you can find all of the information about BIOS tutorials and training. So since the ACE viewer is based on the BIOS platform, if you want more information about how to use the viewer, you should look at the BIOS training. So there's a user guide there, there's some video demos, and then there's also information about live trainings. And finally, for more information about a specific data set, you can click on the little metadata button on the table of contents next to the data set name, and that will bring up a little mini metadata panel on the right that gives you a summary of the metadata. If you scroll down on that panel, it'll give you the link to the fact sheet for the data set. You can also get the complete metadata, and there's also a link to download the data. Okay, so now we'll get into the nitty-gritty of what models are available in ACE. So we already reviewed the data structure, so we're going to go through this in more detail now and talk about each of the components of ACE. So starting out with biodiversity, this is a simplified view of biodiversity. There are actually three components of biodiversity that we looked at in ACE. So one is native richness, so that's based on total number of species in the landscape, both common and rare. The second is rarity, so that's species of greatest conservation need, or SGCN species. And then third is irreplaceability, so those are areas where there are endemic species that only occur in a small area in the landscape. So if you expand out the biodiversity diagram to include all of that, this is what it looks like. So you have biodiversity at the top. There's a combined species biodiversity layer that includes both terrestrial and aquatic, or you can step it down from there in a separate terrestrial biodiversity, which includes amphibians, birds, mammals, plants, and reptiles, or on the right is aquatic biodiversity. And currently the aquatic biodiversity includes fish, aquatic macroinvertebrates, aquatic amphibians, and aquatic reptiles. So further stepping it down from there, you can look at each of the components of biodiversity underneath the overall terrestrial biodiversity. So you can look at terrestrial native richness, terrestrial rarity, or terrestrial irreplaceability, and those same layers with aquatic data. And then you can further step it down to the building blocks at the very bottom, which would be native richness by taxonomic groups. So you can look at mammal native richness, bird native richness, or mammal rarity, bird rarity, plant rarity. So all of those data sets are included in ACE. They're all individual BIOS data sets now, and they're all in the ACE viewer. So here you can see how the data sets are listed in the viewer table of contents. So you have the biodiversity maps here. So you have native richness, rarity, and irreplaceability, and you can expand those open to get the overall summaries and then to get the data by taxonomic group. So you have the summaries, you have data by taxonomic group for each of those summaries, and you have all of that for terrestrial and for aquatic. We also created a climate vulnerable species data layer and a game species data layer. So that's similar to our native species richness, but it's limited to just those species identified as climate vulnerable in SWAP and just those species that we consider to be native game species. Also new in the viewer, which is one of the things I'm most excited about, you can look at the species list to see the list of species that went into the counts for each of those data sets. So if you open up the table for the species list, you can select a hexagon. Whoa. And it'll give you the list of species. It'll tell you whether the information that we have is an observation in the hexagon or HUC, if it's aquatic data, or whether it's modeled to be there. And then you can get more information about whether it's a rare species and was counted in the rarity layer, whether it's an endemic species, climate vulnerable, or game species. So just one note about species data. It requires a lot of quality control. For anyone who's worked with a lot of species data, we put a lot of time and effort into QCing the data that we used in ACE. So we really tried to base it on data that we had high confidence is correct ID, has the correct taxonomy, and is mapped correctly. Okay, so now I'm going to go through each of these data sets individually and just talk about what went into the data and how it was developed, because they were all developed a little bit differently. So we'll start out with native richness. Native richness brings together information on where species and habitats are in the landscape using some of our big CDFW data products. So one is the California Wildlife Habitat Relationship System, and so that has species range data and habitat suitability information for all terrestrial vertebrates in the state. And then we have our vegetation maps created by our Vegetation Classification and Mapping Program. And they've completed about half the state now, I think, and then the best available vegetation maps outside of that area that they've mapped. And so for every full species, both common and rare, we started out with our CWHR range map. So here's an example using California tiger salamander. We took our best available vegetation. We took our species habitat relationships table, and we selected all of the suitable habitat within the range of the species to create a predicted habitat suitability map. So we did that for all of our terrestrial vertebrate species. The aquatic amphibians and aquatic reptiles are a subset of the terrestrial vertebrates. And we don't have predicted habitat suitability yet for fish or aquatic macroinvertebrates because we don't have the habitat suitability tables, and we also don't have a fine enough scale habitat map. So for those two groups, we just used the ranges. So we stacked them all up together, and basically within each hexagon and within each watershed, we counted how many species have suitable habitat within this area. And again, we normalized it by ecoregion. So you're looking at ranging from 1 to 5 areas of high to low native richness in each ecoregion. So in the ACE viewer, you can select a hexagon, and it brings up information about what was mapped in that hexagon. So it gives you the overall ACE rank and ACE weight. So the ecoregion rank tells you how it's rated compared to all of the other hexagons within the ecoregion. The statewide rank tells you how it's ranked compared with all of the other hexagons in the state. And then it gives you the count of the number of species that were counted in that hexagon. So an overall count, and then it gives you the count by taxonomic group. For native richness, it also includes the game species count and the climate vulnerable species count. And here's what the native richness data looks like for the aquatic species. And again, you can select a watershed, and you can get your ranks and your species counts. So that's native richness. Next, we'll move on to rarity. And our rare species richness data was based on documented occurrence data. So that was largely California Natural Diversity Database. We also used some data sets from BIOS. And all of the occurrence data are buffered by 1 mile. So it's a little coarser scale than what you would see if you look at CNDDB directly. One caveat to the rare species richness data is that we don't have systematic surveys of the entire state. So if you see an area that looks like it has low richness, it could be lower richness because there haven't been surveys there. So our rare species richness was based on species of greatest conservation need, and so that's listed species, species of special concern, and fully protected species. It also includes all California rare plant rank 1B and 2 plants. And the species were counted at the taxonomic level at which they're listed. So some of them are at the full species level, others are at the subspecies level. For these data sets, we didn't include aquatic macroinvertebrates because we don't have rarity information for them at this time. So this is what the final map looks like for rarity, terrestrial rarity across the state. And it's a little hard to see on the screen, but there are some areas that are blank, and those would be areas where we have no rare species information. And again, those could be areas where we don't have surveys, or they could be areas where there's low richness. And if you select a hexagon, you again get the rare species rank and the count of the rare species in the hexagon. This is what rare species richness looks like for aquatic species. And you get the same type of data if you select the hexagon, the watershed. So that was rarity. And finally, we'll look at irreplaceability. So irreplaceability is based on the same data as the rarity information, except it's limited to California rare endemic or near endemic species or subspecies. So it's a subset of the SGCN species that went into the rarity layer. And it's also weights each species by the extent of their distribution in the state. So we use the rarity weighted index, which basically gives each species a weight based on the number of hexagons or the number of watersheds that they occur in. And so here's what the irreplaceability summary looks like. And if you select a hexagon, you get the number of species that went into the counts. And similarly for aquatic, you can select a watershed. So that data was then rolled up into the overall terrestrial biodiversity, aquatic biodiversity, and overarching species biodiversity information. So terrestrial biodiversity, I just wanted to show that if you use this layer, this will give you all of the ranks and weights and species counts that were included in all the 3 sublayers that I just showed you. So if you want to see everything at once, you can use the terrestrial biodiversity layer. And similarly for aquatic biodiversity, it's similar, so you get all of the information that went into that overall biodiversity layer. Finally, the overarching biodiversity layer, this combines hexagons and watersheds together, and this was a methodology that Ryan Hill developed. He's helped script ACE, and he developed a methodology to bring together the aquatic and terrestrial boundaries so that we can see both on the map at the same time. And so if you zoom in, you can start to see that you still see the hexagon boundaries, but you also can see some watersheds highlighted out here too. And one note about this is that aquatic reptiles and amphibians were not double counted. So they're counted in both the terrestrial and the aquatic layers, but in the overarching layer, they aren't double counted. And for the overall species biodiversity, if you select a hexagon, you get the name of the hexagon ID, the name of the watershed, and then this gives you all of the ranks for all of the data layers that we developed. So it gives you the overall biodiversity rank, the terrestrial, the aquatic biodiversity rank, and so it gives you sort of a one-stop place where you can look at all of the ranks and compare them. We also, at the end of the table, included the ranks for connectivity, climate resilience, and significant habitats, and we put this abbreviation SUP for supplemental at the end of that, because just to note that these didn't actually go into the calculation, but they're just here so that you can see all of the ranks in one place. So that was biodiversity. So now we'll talk about significant habitats. So how did we choose significant habitats? They're actually based on habitats of conservation priority or habitats with regulatory protections. So our list included rare vegetation types. Oak woodlands was new in ACE 3, so we hadn't considered that one in ACE 2, but we did add it in ACE 3 because it is of high conservation priority. Then we had riparian, some different types of freshwater wetlands, saline wetlands, lakes, and then significant habitat areas for focal species. Right now, what we have in ACE 3 is significant habitat areas for anadromous fish, and we're working on adding additional species in phase 2. So the significant habitat summary gives you a rank from 1 to 5 based on the number of different significant habitats present in a hexagon or watershed. It does not consider the area of the habitat or anything more detailed than just is the habitat there or not. And then you can look at each of the individual significant habitat data layers also in the viewer. So if you select a hexagon, it'll tell you yes or no, is the significant habitat type present in the hexagon. So here you can see that rare vegetation, yes, there's rare vegetation mapped in this hexagon. There are vernal pools mapped in the hexagon. And so then what you can do is you can go to your rare vegetation type data layer, and it'll tell you which map is actually mapping rare vegetation in that hexagon. And so then you can put your data layer into the selection box at the top and find out more information about that data layer. You could also overlay it onto the ACE viewer to find out exactly which rare vegetation types and where they were mapped in the hexagon. So similarly with vernal pools, it tells you which data set that came from. And so aquatic is structured similarly. And here I just wanted to show that for the anadromous habitat, you can see here there's no anadromous habitat mapped. So one thing you might want to do is then look at where is the significant anadromous fish habitat, and you can see that it's actually right next to the watershed that you're looking at. And so then if you select that one that's next to your watershed of interest, you can see which anadromous fish are present there and what data set did that come from. So that's significant habitats, and then we'll move on to, so everything here on the right is the new data sets that we added in version ACE version 3. So we'll start out with connectivity. So back when we were developing ACE 2, the California Essential Habitat Connectivity Project was being developed in parallel around the same time in 2009. And so at the time, we had identified connectivity as a really important component that we should consider in ACE, but we didn't have a statewide map. And once the CEHC, or the California Essential Habitat Connectivity Project, was completed, that's been available as an overlay in the ACE viewer since then. And so what the CEHC did was it identified a couple of different things. So one is it identified remaining contiguous blocks of natural habitat within the state, and so those are the large intact blocks. And then it identified habitat linkages that link those blocks together. So we wanted to incorporate that into ACE, but we also knew that since that's been done, there's also been a number of regional connectivity analyses that have looked at a much finer scale region and have used species-specific information to map corridors and linkages. So we wanted to pull all of that information together. In addition to that, we also have a landscape intactness layer that was recently developed. I think it was published last year by the Conservation Biology Institute. And so that's an update to overall landscape intactness in the state. And so what we did was we used a rule set based on these data sets, and we looked at percent of the hex that's in the landscape block, the level of current intactness, and also how much of the hex is in a corridor. And so we used that to rank the state, to give the state a connectivity rank between 1 and 5. So it's a snapshot overview of the connectivity information that has been mapped in each hexagon. And you can select a hexagon, and it will tell you what the ranks are. It will also give you a link, or tell you which linkage data sets mapped connectivity within that hexagon. And it gives you a landscape block rank based on the percent of the hexagon that is in a large contiguous natural area. So those ranks those connectivity ranks from 1 to 5 are not really for use in additional analysis. You'd want to go back to the original data layer, but they give you sort of a contextual statewide view of what connectivity values are and how they're spread across the state. Another thing I wanted to mention is that on our main BIOS webpage, we put together a BIOS habitat connectivity viewer, and we added all of those data sets to the BIOS habitat connectivity viewer. So you can go there to get access to all of those habitat connectivity data sets that we compiled for this effort. So now moving on to climate resilience. The climate resilience data for now is based primarily on the climate change vulnerability assessment of terrestrial vegetation that was done by Jim Thorne's group at UC Davis. And so they looked at a number of different future climate scenarios that ranged from hotter and drier to warmer and wetter in the future. So they kind of ranged the gamut of which trajectory the climate could take in the future, and we're still not exactly sure which one it will take. And so we brought those models together, and in order to help reduce uncertainty, we ranked hexagons based on the number of models that predicted there would be climate resilient habitat within the hexagon, and also how much climate resilient habitat was predicted to be in the hexagon. So areas that are ranked as 5 here, high climate resilience, they are showing climate resilience regardless of which trajectory the climate takes in the future. And this is the climate resilience data set is a work in progress, so we're continuing to work on that for phase 2. And here you can select a hexagon and you can see what the score is and also the percent of the hexagon that was assessed by the project. So if you dig into his project a little bit deeper, they didn't evaluate urban or agricultural or open water. And so some hexagons, they may have a score, but only a portion of the hexagon might have been assessed. And finally, recreation. So recreation is another work in progress. So recreation, it could be hunting, it could be fishing, it could be wildlife viewing, hiking, basically any outdoor activity. And so we're trying to pull together as much information as we can on recreation and pull it into the ACE viewer. So it's not in the viewer yet. Right now, the recreation data that we have compiled is on our website. And there are links on the website to a couple of different resources with recreation data. So there's the Disadvantaged Communities Mapping Tool, and then there's also a BIOS viewer that has recreation data. It has all of the recreation data sets preloaded. And so in phase 2, which is coming up, we're going to be working on how to best integrate that information into the ACE viewer. So finally, we have our overlays, starting out with SWAP. So the SWAP, our State Wildlife Action Plan data, is based on the targets that were identified in the State Wildlife Action Plan that was published in 2015. And Diane Mastelier, the SWAP GIS person, did a great job creating a spatial data set to go along with SWAP. And so that's available now in the ACE viewer. So here you can see the SWAP terrestrial targets. And if you select an area, you get information about the SWAP province and where in the document, so which chapter the data is found in. It gives you information about the name of the target and then the page numbers in the document that refer to that target. And if there's more than one target mapped, it gives you the information about multiple targets. It also gives you a list of all of the possible targets that could be in an area. So there may be some areas where, because of the scale, the way that things were mapped, it doesn't necessarily show up on the map, but when you go out in the field, it might be there. So this could give users a list of potential targets to look for when they're out in the field in a certain area. So this could be really useful for grant proposals that need to refer to SWAP information and SWAP targets. And so you can overlay this information onto ACE as well. So next is stressors, and stressors is another component that we're further compiling stressor information for phase 2. For now, we have sea level rise projections, and the projections that are in the viewer right now are the projections from the state third climate assessment. There's actually an effort underway right now to remap the sea level rise projections for the fourth climate assessment, and those are supposed to come out later this year. And so when they do, we'll be replacing the data that's in the ACE viewer. And then we also have a new land use change probability map that was developed by USGS in cooperation with the state of California that is also available. And then finally, land conservation status. That is found down in the reference layers at the bottom of the table of contents. So if you scroll down there, you can see all of the land ownership data sets that you may want to look at along with the ACE data. So that's all of the data. So now I'll run through a couple of example scenarios of how you might want to use the data in the viewer. So some uses of ACE might be to identify the conservation elements present at a site, to compare the relative value between sites, or to evaluate the location and relative juxtaposition of those elements and land ownership, stressors, et cetera. So we'll use an example at San Antonio Creek Watershed, which is in the Bay Area. It's between Livermore. So Livermore's over here, and here's San Jose. So we'll take a closer look at some of the information we could find out about this watershed using ACE. So first we can look at species biodiversity. We can get all of the ranks of the watershed and look at how it ranks on an ecoregional basis and also on a statewide basis. And so you can see here that overall the ranks are quite high. They're mostly 5s and a couple of 4s. So it's pretty high ranking. You can get the information on the number of species that have habitat mapped within the hexagon. So you can look at native species, rare species, and endemic species. And then you can open up your species list and see what species have been mapped in this hexagon or may have suitable habitat in the hexagon. You can do the same thing with the aquatic species list. So you can see the aquatic species present in the watershed. And then you could take a look at which significant habitats might have been mapped in the hexagon. So you can see that there is no rare vegetation, but oak woodland and riparian have been mapped in the hexagon. And so then you can go down to those maps. This is the oak woodland map, and you can find out which maps have mapped oak woodland in this area. And so then you can even overlay the map and look at it in more detail if you want to. And similarly with riparian. And then you can look at connectivity. So you can see the connectivity rank is very high. So the connectivity rank goes up to 7, and it has the highest rank possible. And then you can overlay the various connectivity data layers. So here is the natural landscape blocks from the California Essential Habitat Connectivity Project. So you can see that almost the entire hexagon, so 95%, is mapped as a natural landscape block. This is the statewide essential connectivity areas, so they barely get into the hexagon. But if you overlay the Bay Area linkage network, you can see that there's a corridor mapped that goes right through the hexagon. And then you can look at how climate change resilience is mapped, the SWAP targets. So you can see that the SWAP target in your hexagon is California grasslands and flower fields. And you can look at the list of other possible targets that might be present. So American Southwest riparian forest and woodland might also be present. So you can use all that information then to compare relative value between sites and to evaluate relative location. And so we can do that here. So here's our watershed again, and here I've overlain conserved lands. And so you can see that there's an area up in the north that is not conserved, and an area kind of going through the middle of the watershed that's not conserved. So then you can start looking at what values these different areas have. So if you look at your hexagon in the north, you can see what your biodiversity ranks are there, and what your biodiversity ranks are in a hexagon in the southern part. And you can see that they're very similar, which makes sense for the biodiversity data because it's areas that are very close to each other are likely to have similar values. So since biodiversity is pretty similar, what else might you look at to try to see what the difference between your two values are, between your two areas are? Well, one, if you look at your connectivity, you can see that your corridor is running straight through your this lower area, and there's no corridor mapped in the upper area. If you look at projected urban and ag expansion, you can see that there's projected urban expansion in the north, and none projected in this southern area. So those are all things that may help inform your planning, depending on what you're doing. You might use the information in different ways, and so that's one of the reasons that we kept all of the data layers separate. We haven't, at least not yet, compiled them all into a single score, because how you view the data and how you might use it really is going to differ depending on your particular project. So finally, I'll just talk about where we're going in the future. We're now starting to work on version 3, phase 2. So what I just showed was the version 2, phase 1. In phase 2, we're focusing on the connectivity data, the climate resilience, recreation, and the aquatic data. So all of the new data sets, if you remember, these are all the things that we actually added in version 3. We are planning to work on further. So we have a first draft, but there's still a lot more work to be done. And we are still planning to do regular updates, at least annually. So I've already gotten some questions. How can I submit my data to have it incorporated into ACE? So one way to do that is to submit your data sets to BIOS. There's a website that shows you or explains how to do that. If when you submit data to BIOS, you'd like to have it considered an ACE, make a note of that, because we are adding BIOS data sets on a case-by-case basis. But if the submitter would like to have it included, then we can definitely prioritize that. Another way is to submit your data to CNDDB using the field survey form. So if you have rare species data, that data is automatically added to ACE. So whenever we do an update, we get the most recent version of CNDDB to put into that update. So if you submit your data to CNDDB, it will automatically be added to ACE. And finally, you can contact us if you have more questions or would like to talk more about submitting data. So everything I went over today is on our website, and so there's a lot of documentation there, a lot of resources, but you're also welcome to contact either myself or Karen Miner if you have additional questions. And that's all I have. Thank you.